Now we're going to talk about putting these together. So not only we talked about carbohydrates, but now we talk about how they can go together. So these are going to be glycosides as they come together. We're going to have things like disaccharides, as you might imagine. They're going to be the simplest oligosaccharide. It's a reminder that oligo just means few. So whenever we talk about this is putting them together. A disaccharide is going to be two monosaccharides linked by a glycosidic bond. So again, you're noticing some of that terminology and some of those prefixes coming back. We're going to call each unit in that oligosaccharide a residue. So just like when we were talking about peptide chains and proteins, we could refer to every amino acid as a residue. Now that we have chains of sugars, chains of carbohydrates, we can still refer to each individual one as a residue. When we look below, these are all mixed acetals, where you have one hydroxyl provided intramolecularly and one from the other monosaccharide. And as you look at these, what you'll notice is that most of them are using the anomeric carbon, or the carbon that was originally the carbonyl carbon before it was cyclized. So you have that first carbon of the anomeric carbon, and then it's using some other carbon of the other sugar, except for sucrose. So you're going to also hear that a lot, where we have a lot of things that are very similar between a lot of disaccharides, and sucrose is going to be different because sucrose is formed by using both of the anomeric carbons. So since both of those anomeric carbons come together in sucrose, it's a bit different. What that means, though, is that when we have that anomeric carbon that is free, so you see here all of the green highlighted pieces, those are going to be reducing sugars. The name reducing sugar does come from the ability of different carbohydrates to reduce different metals. So that is where that comes from. But for us, what we're going to basically look at is if it has a free anomeric carbon, then it is a reducing sugar. Because sucrose has both of the anomeric carbons forming that glycosidic bond, sucrose does not have a free anomeric carbon. Also, as you look at these linkages, notice that when we're talking about them, we're naming them for whatever sugar is using its anomeric carbon first. So we're looking at lactose. It's galactose beta 1. So that beta is telling you that anomeric carbon, it is the beta form of that particular sugar. And then it's connecting to the fourth carbon of the glucose molecule. So it's galactose beta 1 for connecting to the anomeric carbon of the galactose residue that was, when it was cyclized, was in the beta form of galactose, then is connecting to, for glucose, the fourth carbon of the glucose molecule. When we do form a glycosidic bond, this is going to be another dehydration reaction where we're eliminating water between two hydroxyl groups. And when we're looking at this, because again, we are using only one anomeric carbon, we're using that from a glucose residue. So these are just two glucose residues. I know it's the fancier term of the glucose pyranose. So just to remind you that that's glucose in a 6-membered ring form. And since what we're using is one anomeric carbon attached, in this case, still to that fourth carbon, you guys can try to think for yourselves for a minute what that name would look like. Another example, but now what we have is we're forming it with the beta. So if we were instead using beta instead of alpha, our original starting monosaccharides would have this particular shape, where then you have the beta form with that hydroxyl group pointed in that up position. So then we're actually looking at these. So now here they are together. So for those of you who are trying to figure out what it was, so maltose is when you have two glucose molecules together, but they're using the alpha form. And cellobiose is when you have that same general idea, but then we have a beta linkage. So maltose has an alpha linkage, which means that anomeric carbon was in that alpha position. Cellobiose then had it in the beta position. So as we're going back through, this combination would have given you maltose. This gives you cellobiose. So you actually get two different disaccharides depending on what the linkage is. So the linkage in between these also makes a big difference when we're looking at how these things come together, what we name them, how it works. So even though everything's the same, just that linkage in between them is different. Also note that when we're talking about that reducing end, that anomeric carbon could be alpha or beta. So you'll notice that those aren't actually shown in one way or the other. They're kind of shown in this either or. That's because it can be either or. So since we were just showing off the difference between alpha and beta on the previous slide, this one is still keeping with that maltose example. But now what we were looking at before had everything linked to the fourth carbon. Now we're actually linking to the sixth carbon in isomaltose. So notice that it is still a version of maltose because it is still an alpha linkage. But now we're actually linking to the sixth carbon. So we call this isomaltose. And again, the only difference here is that it's linked to a different carbon on the glucose ring. Looking at lactose, again, very, very similar. Disaccharide, a beta linkage, and we're using galactose. Here, the glycosidic bond is hydrolyzed by lactase, and that would actually get you then that molecule of lactose and that molecule of glucose. Lactose intolerance is a fairly common human condition. It's caused by a deficiency in lactase. So it's actually caused by a deficiency of the ability to break that bond, to break the bond of that disaccharide. So go ahead and take a minute. So would you serve this to someone who's allergic to lactose? So not just lactose intolerant, where they're missing the lactase enzyme, but as an actual allergy to lactose. For those of you that don't have any friends that may have this, there are a variety of different proteins, especially in milk, that different people can be allergic to. So in this case, I'm kind of formulating like, well, what if they were allergic to the lactose? My friend who's allergic to milk is actually allergic to a different protein in milk. That's not the sugar. But this is just kind of that fun what if question. So looking again back at sucrose. So this is another disaccharide. So we can see its linkage name there. This is a molecule of glucose and a molecule of fructose. But because both of the anomeric carbons were used, there is no anomeric carbon left. And so this is not a reducing sugar. And it does take then sucrase to separate these back. So sucrase is an enzyme that will separate these into glucose and fructose. These names are really easy to misspeak, so I apologize for me going back over some of these.